Hello friends. So last class we have started with the laser working principle and what are the different types of laser we can use. One is the fabricated laser and another is the distributed feedback laser. Okay. So when you want to build the laser working principle, so we need a active media and some fundamental modes are required. If you remember this thing, we need a active media and inside the active media there will get some resonance frequency. So we need to emit the maximum number of the photons, right? So through the media we can produce the different number of photons and all the photons should be in the same phase and when you want to build the coherent light from the laser, right? So for that you need the cavity, right? The active media, if you think about the active media it is the cavity. Okay, okay, the active media it is the cavity. Okay, so both mirrors are the reflectivity is there, so it is fully reflected in the partially reflectivity is there. Okay, so photon first it will go to upper state. Then when it come back to the when it try to come back to the lower state, it will not come back to the lower state. It will keep that interface and again it will come to the this interface. When all the so suppose 4 5 number of photons are reached at this interface, then the all the 4 5 photons which has the same frequency will emit. Okay, this is the normal principle of the laser. So the cavity, so how the way the photons are propagating through the this active media. So this concept is called the cavity. Okay. So the modes of the cavity. So how the resonance, how the optical cell or photons are propagating through the cavity. So this, if the photons are propagating through the cavity, so there will be electrical and magnetic distribution. So the pattern of the electrical magnetic distribution is known as the cavity. Okay, so there are the longitudinal cavity, lateral cavity, and the transverse cavity. The longitudinal cavity that is related to length of the cavity. Here it is mean the lateral is lies in the plane of the p-n junction. The transverse mode cavity that is associated with the electromagnetic field and beam profile in the direction. So this I will discuss in the with the help of the diagram. Okay. Normally we used to prefer the longitudinal mode or the transfer mode. Lateral mode we don't used to prefer sometimes if you want to get a proper the mode. Okay. So the different types of the mode they have different optical paths. So we get sometimes the sometimes the all the photons will not have the same frequency. Some photon will have the same frequency and those photon will come out from the device which will give the high gain. Okay, so the next slide show the some diagram. Okay, so here you can see this is the longitudinal mode. So this is the active media. There will be the mirror. Two different mirrors are there. The end mirror. This is the output coupler. So from this mirror, the output will come out. Right. So here in this case of the longitudinal mode, you can see uh, there are two distinct. So the both the so there is one red line and there is one dotted line. You can see. So both the wavelength, both the photons will not have the same wavelength. Both the photons have the different wavelength. Okay. So that means when all the photons come out from the device, both the photons should be in the same wavelength. Otherwise, you will not get the high gain. Okay, so the suppose two photons are coming, falling from the upper state to lower state, and during that time, the two photons will hit the this interface and mirror interface. Okay, so due to that, what will happen again? It will hit the interface, and it will again it will propagate back to the this interface. Okay, so when it is coming out, the two different photons are propagated at a different time because this their wavelengths are not different, same. Okay, but so for these wavelengths, some more photons will be there. For these wavelengths, some more photons will be there. So all the photons will come out from the device. This is the longitudinal. So normally the this will propagate to the mirror. Okay, so you can see in the longitudinal mode, and there is the transverse mode. Okay, but almost the same. What is the main difference that I will tell? Okay, so here you can see. So whatever photons are proper hitting this and the mirror in the perpendicular way. So some photons are hitting in the mirror in this side on this side. This will lost. Those photons will lost. Whatever photons are hit in the end mirror in the perpendicular way or longitudinal way, those photons will come out from the device as these are proper achieving the high gain. Okay, but in this case you can see the mirror, this mirror and this mirror, both the mirrors are designed such a way that when the photon will come out from the upper state to when the photon will fall, try to fall from the upper state to a lower state, from the upper state to lower state, then what will happen? Upper state to lower state. Then some photon will hit this interface in the perpendicular way. Some photon will interface in this point. So whatever photons are interfacing this point, this point, this point, this point. Okay. So all the photon will reflected back from the mirror and both will again come to the this mirror. Okay, in this and both all the photons will hit this mirror and all the photons will come out from the device. Okay, so you get the different directions. Here you can see in the same directions both the photons are coming out, but both photons have the different wavelength or different frequency. Here you can see the different direction the photon is coming out. All the photons have the different direction. Okay, because some photon hit in this point, some photon will hit in this point, some photon will hit this point, some photon will hit this point. So whatever photon will hit the this end mirror, all the photon will oscillate and the hit this interface and all the photon will come out. So we have to design the media cavity such a way that all the photons, whatever photons are hit at the opposite interface, all the photons will come out from this mirror. Okay, so this is about the transformer. So here the different kinds of the configuration you can see when you see the laser light from the this opening end, coupling end, you can see the mode. Okay, different kind of the mode you can see TM00, TM10, TM01, TM like that. So this you can see this is the corresponding diagram. Okay, so here also it keeps the interface and it's coming out. It's saying. So in this way it is going on. In the each and every point the mirror, the photon will hit the mirror. The lateral mirror that is the perpendicular to the longitudinal. Okay, the photons are traveling in this direction. Okay, photons are traveling in this direction. In the lateral mode, photons will be traveling in this direction. Okay, so we normally used to prepare the transverse mode as well as the longitudinal mode. Now come to the laser operating for operation and the lasing condition. Some lasing condition means so at some after some point. So in the device you can see suppose the absorption will happen if you recall the previous working principle. First the absorption will happen inside the device, then the after the exhaustion, then there will be the uh, stimulated emission. Then there will be the sorry spontaneous emission. Then there will be the stimulated emission. Okay, so stimulated. So for achieving the stimulated emission, you have to create a one gain media, and the mirror should be there. So the moment when the stimulated emission should be start. That moment, that point is called as the lasing condition. Okay, before that, so nothing will be there, nothing will be generated from the laser. Okay, so here you can see there is one equation that is E is equal to Z comma T I Z is equal to j omega T minus beta Z. Okay, so the photons, the both are corresponding to their own electromagnetic wave. Okay, so if you want to represent the equation for the photon, so you can represent like this way, which the photon is propagating with respect to time as well as with respect to distance. Okay. So whatever photons are there, those photons are exponentially decay over the distance by a factor of the g, and it is attenuated by a factor of the alpha. So so when photon propagates to the active media, so there will be some attenuation. Sometimes there will be a amplification. So the amplification factor that will be more as compared to the attenuation the factor for getting some gain. Okay. So if attenuation is more and amplification is less, then there will be no gain. The gain will be less very. But if the attenuation is less, the amplification is more, then the resulting gain will be the more. Okay, so the radiation intensity of the photon that will vary exponentially over the distance by a factor of the gain factor by a factor of the attenuated factor. Okay, so in this way we can write the equation for intensity is like that. So this is the equation. Okay, so Iz is equal to I naught e to the power, but that's tau z h nu minus alpha h nu into z. That is over the distance how the photon is propagating through the device optical media. That this is the amplification factor. This is the attenuation factor. Okay. Now, what I told that you can see in this diagram, you can see suppose the one photon try to come from the upper state to lower state. Okay. So suppose there is a photon, this photon will come up from will fall down from upper state to lower state. Okay. So before, so in the active media, what used to happen that it will not fall into the down state. It will hit this interface. So it is the reflectivity is such that it will not absorb the photon or it will not penetrate the photon. It will what it will do. It will the photon will hit and the photon will reflected back from the this interface. Again, it will go to the this interface. Okay, again it will the photon will come into this interface. Again, it will go. So you can see there the distance photon covered by the distance covered by the photon. So suppose L and then 2L. Okay, or L and then 2L. So first it will hit this one and then again it will come this one. Okay, so normally one photon for achieving the minimum condition, photon should be hit this interface and then it will come into this interface. So normally the 2L distance should be covered by the photon. Okay, that's why, so suppose the intensity at initial moment of the photon I is 0. Okay, so suppose here Z is the 0. Okay, so at I 0, so then the photon is hitting here and again hitting here, like this way it used to happen. So at initially the photon in the wherever the photon will situated, initially the photon the location will be 0. When it will hit and forth and back, one step of forth and back for achieving the one step of forth and back oscillating. Okay, it need to cover the 2L distance. Okay, it need to cover the 2L distance for one step of forth and back oscillation. Okay, so then the Z will be the 12. Okay, now the I0. So here we have multiplied the term with the, you can see the this term we have multiplied with the R1 and R0. Okay, R1 and the R0. Others are same, only Z we have replaced with the 12, the amplification component, optical component factor and the gain coefficient. Okay, therefore, if you multiply tau and the g, we will get the total amplification factor. And the alpha is the effective absorption coefficient or the attenuation factor. Okay, so this is the intensity after the photon traveling the 12 distance. Okay, so why I have multiplied the R1 and R2 depends on the reflectivity. It will decide whether photon will the absorb or photon will penetrate. That's why the R1 and R2 this reflectivity should be multiplied with the intensity. Okay, and then reflectivity of those both the mirror should be calculated as a n1 minus n2 divided by n1 plus n2 whole square. Okay, so when there will be the lazy condition. Okay, so you can see then the minimum gain should be greater than 1. Okay, then there will be the proper Lagrange condition. You will get the coherent light. If there is a no gain, then there you will not get any coherent light. So minimum gain should be greater than is equal to 1. So gain is equal to 1. What is the gain? Gain is the I output by I input. I Z by I naught. What is the I Z? I Z is equal to I 2L by I naught. Okay, I 2L by I naught. So I naught is same only. Instead of I 2L, you can put this equation. And I naught, this I naught will cancel out. So you can get the gain is equal to this equation. Okay, R1, R2, the exponential, the extra term you will get. That is equal to will be on 1. So that means for achieving the greater than gain is equal to 1, your I12 should be equal to I naught. When the gain is equal to 1, if you are getting the same intensity, point at the initial one. So if the photon, so suppose one photon is generated, the same photon should come out from the device. Okay, so then the gain should be the same. Okay, the gain should be equal, and when gain should be equal, I2L is equal to I naught, and the phase is also is equal to the one. Okay. Okay. So what I told, if the gain is equal to 1, if you put the I2L is equal to IZ, then you will get a this equation. If you substitute this one, the tau G, the threshold, the gaining factor, that is equal to alpha plus 1 by 2L ln 1 by R1 plus R2. So the laser starts to lace only if the G greater than is equal to GTH. The that time moment only the stimulated emission will be take place. Okay, so this gain also you can represent the gain as a beta into JT. So the beta is on factor JT is the threshold current density. This much current you have to provide into the laser so that the stimulated emission will be take place. There will be the strong carrier confinement, there will be the strong optical confinement. When you apply the threshold, this much threshold current JT, then only you will get the threshold gain, and then only the stimulated emission will be take place. Okay, so again, what again I told that the phase will be also is equal to 1 for achieving the for getting the resonance frequency and the coherent line. This the e to the minus j 2 by 2 beta should be equal to 1. If you write this is equal to 1, you can by the mathematics formula you can write as a 2 beta is equal to 2 pi m. The beta is equal to 2 and pi by lambda. Okay, and this is the resonance frequency. The lambda is the resonance frequency of the nth order mode. Okay, so again, if you substitute this one, the frequency. Okay, the frequency you will get as a the lambda. This is the nu. The optical frequency you can represent as a nu. Nu is equal to mc by 2l lambda. Okay, mc by 2l lambda. Okay. So if you substitute the equation, you will get the mc by 2m lambda. So that means if you and mu m, the frequency m is equal to the for m is mth order mode. Okay, for mth order mode, the frequency is mc by 2ln. For m minus 1 order mode, the frequency will be m minus 1 c 2lm. If you substitute this one and this one, so mth order mode what will be the m minus 1. Okay, m minus 1 c 2ln. Okay, so if you substitute these from these, you will get the c by 2lm. So delta lambda. So normally, if you see the graph, I'll tell in the next slide. The graph is like that. So there will be there for different wavelengths, you will get the some gain. Okay. So for corresponding, so this is one fundamental mode, this is one fundamental mode, this is one fundamental mode, like that. The difference between two fundamental modes, okay, it's equal to c by 2l lambda. Sorry, lambda square by 2lm. Okay, again you are converting the equal putting the c, the f in terms of the c by lambda, will get this one. Del lambda is equal to lambda square by 2n. So this is the lambda versus the gain graph. Okay, lambda versus gain graph, you will get the this is the del lambda square by 2l. The frequency deviation. So for each mode. Okay. So you can see that the gain versus the wavelength curve. So this is one fundamental mode, this is one fundamental mode. So all the fundamental mode, for now you can also see that for some wavelengths you are not getting the high gain. Okay, for some wavelengths you are getting the gain. So again, if you want to represent the gain with respect to wavelength, the g lambda is equal to g naught to the power minus lambda 2 by 2 square. You can see the wavelength is changing. The gain is changing with respect to wavelength exponentially. Okay, gain is changing exponentially. In that, before two slides before also we told there is a formula the where the intensity will be decreased exponentially. Okay, so this is the factor. So del lambda is the this one whatever I told lambda square by 2 and lambda. The Gaussian shape of the parts we can get. So sometimes, so just consider the some fundamental mode which have the high gain. and there will be a threshold level below that, or other fundamental mode will don't have the high gain. That means suppose in a media the different wavelength photons are getting the different wavelength photons, not all the photon will maintain the standing wave. Some photon will maintain the standing wave. Those are the fundamental mode. And from the fundamental mode, all the standing wave will not produce the high gain. Some standing wave mode, fundamental mode will produce the high gain. In these two, we can get the coherent line. Okay. So I think thing is clear. The next class, I will again discuss one more laser equation followed by some numerical. Thank you, and please like, share, subscribe, and share my channel.